fait, c'est le dernier séquence. Bonjour à tous. Est-ce qu'en ligne, vous m'entendez bien là?
Tu veux dire rien?
Donc, on a le plaisir d'avoir Clémentine Gritti pour le dernier séminaire avant les francopholies l'été. D'ailleurs, on a réussi à avoir Ariane Moffat qui a fait un pré-concert avant, apparemment sur l'esplanade tranquille. Donc Clémentine a beaucoup de mobilité, mais je vais la présenter ça, mais elle est actuellement chère professeure junior à l'INSA de Lyon et elle travaille sur les enjeux d'apprentissage fédéré, comme elle va nous en parler, et de sécurité. Un background aussi en cryptographie assez fort, donc peut-être
Oui,
voilà, je vais pas prendre plus de temps.
Si, c'est vaste. Bonjour à toutes et à tous. Donc déjà, je vais parler en français, si ça va à tout le monde. Les diapos sont en anglais.
Anglais.
Hein? You prefer English? Yeah, okay, I can switch to English. And you, of course, you can interrupt me, ask questions during my presentation. We don't need to wait until the end. So I start to present myself. Sebastian didn't need to do it. I traveled quite a lot. I did my PhD in Australia. I did 2 postdocs, one in France and one in Norway. I was a lecturer at the University of Canterbury in New Zealand. So lecturer is like, assistant professor. I had to go back to France. Well, it was still a choice, but it was difficult. So I needed to do a first postdoc like that. I could network first. And then I found the chair professor junior. It is a tenure track position in Lyon. And it's quite new in France, this kind of position. Usually, you become a civil servant in France, so you are protected your whole career. But now it's 5 years, and at the end of the 5 years, I need to prove that I can be a professor. So let's see. I started last year. Not too stressed yet. So I have been working on public key cryptography. So mostly based on the elliptic curves, because some of you are aware of this kind of cryptography. So for the PhD, it was linked to the electronic health. Then the postdoc at Eurocom, it was Internet of Things. The postdoc in Norway was electronic voting. I did a little bit of blockchain and moved towards post-quantum cryptography when I was in New Zealand. And when I came back in France, I started to work on applying cryptography to federated learning. And today I will show you what I have done so far since I'm in France. So when we say cryptography for federated learning, it's mostly related to secure aggregation. So federated learning, we have multiple clients. They are asked to train a global model, and once they get their results, they send them to a server. The server is in charge of aggregating the results, and it gives a new global model that is sent back to the clients, and the clients start again, train on that global model, get results sent to the server, aggregate, and so on, until you reach an accuracy that you think is good enough. So, as the way I said, we just send our results. So we have the device blue, the device red, and the device green. The brain represents the results they got from training, and you aggregate. So we do a sum. And so you get a new global model that takes into account all the inputs received from the clients. But here, everything is in plain. we must trust the server because the server has been shown that it can infer some private information from the results inputs sent by the clients. So that case is when we trust the server, but we should not trust the server. So we need to protect the inputs of the clients. So here indeed from the figure I drew, it looks like encrypted, but you have other techniques. Indeed, I will mostly talk about encryption today. And the idea of protecting the individual inputs from clients, aggregating them in their protected form is called secure aggregation. But at the end, the server doesn't get a global model that is still encrypted or protected. He has the capability to get the global model in plain, and once he gets it in plain, he sends it back to the clients. So the clients protect their individual models, so like that the server cannot infer any information from them, but the server gets access to the global model from aggregating the protected individual inputs. Yes.
Je vais poser la question.
Oh, yeah.
Pourquoi c'est important que le modèle soit clair, le modèle résultant soit clair? Il peut aussi être encrypté aussi.
Indeed, the global model could be encrypted, and we could imagine that the server sends the global model encrypted to the clients, and the clients are in charge of decrypting it. But yeah, the scenario I'm focusing on allows the server to get access to the global model because we assume that the global model doesn't give information from the local input. It's a mix of enough inputs like that the global model doesn't reveal any sensitive information from the client. So we allow that. Okay, so some background from crypto before I show you what has been done and what we did with my colleagues, Ricardo, Melek, and Marco. So secure aggregation can be split into two groups, encryption and multi-party computation. And I highlighted in red the techniques we used. So we did masking. To say it's a little bit like adding a noise. You add something to your input and it's masked. You don't manage to understand what was the original input. I will show you additively homomorphic encryption. So it means that we can, it represents the figure I showed you before. So we have the inputs, they are protected, encrypted, and we can do the operation sum on them to get the global model. And some secret sharing techniques, because we will see that we cannot rely on all the clients all the time. So we need to be sure that for the remaining clients, they have enough information from others in order to complete the aggregation with the server. Okay, so starting with secret sharing, that's the idea. You split a secret into multiple shares, so let's say N, but your scheme is built such that you need only T pieces to reconstruct the secret. Even if you have N pieces in total, you can use T, at least T of them to get the full secret. So that's the idea that on the figure, we have 3 points. We draw that line from 3 points, but if we want to reconstruct that line, we need only 2 points. So that is a technique we will use. Then secure aggregation using masking. So that's I forgot my picture. So every mask is shared between one device, the owner, with the other two. So that is the mask they construct between device blue and device red, that one, and that one is between device blue and device green. Okay, so everybody has two masks because there are three in total, so you need to have two. You need to share something with the two other devices, and you mask your input using the mask you built with others. And such a way, there are some rules behind to say if you need to put a minus or a plus. But at the end, when we aggregate, we do the sum, they should cancel out. Yeah? So all the masks disappear, and we get our global model. Yeah? That is when all the clients that register at the beginning in order to compute those masks are still online. Yeah.
So you assume that before the trusted server comes, there is each of the clients are able to communicate with each other to like create the pairwise.
Yes, there is a setup phase where maybe you need a trust party to help you to connect to the others. Or it's not, yeah, there are still some assumptions at the beginning to make it work. But the device red, he missed the round, he didn't submit anything. Maybe he became offline, maybe it was too slow to submit the input on time because you have the idea of a round is defined by a time window, and so the server to launch the aggregation waits until a certain time, and after that time it triggers aggregation, but hoping to have received all the inputs on time. Most of it failed. And so the other two, blue and green, they did as expected. They masked their inputs as defined by the system. And so we cannot cancel. So we add the blue and green, but we cannot cancel the mask that are in common between red and blue and red and green. So we don't have a global model. It's a global model with some noises. The masks are makes the result not usable. So some solutions propose to anticipate that some clients will drop, and so they need again at the beginning when they register to secret share their mask that they have in common with others, but then they need to secret share with everyone. Like that, remaining clients will reconstruct the missing mask, and so aggregation will be successful. So red has secret shared. Well, so here it's only two devices, but you need to think about multiple devices. So the pieces of his own masks sent to everybody else. So good for that. And then, in addition to masking as usual using the pairwise mask, you add the pieces of the mask of the drop client, and that's in the middle. And reconstructed during the aggregation. It doesn't matter that we don't have the input from the device red. It's like null, empty. But at the end, what we really wanted is to be sure that all the masks were cancelled out. So at the end, you have the global model with inputs from blue and green, nothing from red, but you don't have mask that mess up the result. Yeah.
To do so, you need to reactive to the fact that you detected that one to.
Yes, indeed. So it's not a one-time short communication. There are a lot of communication between the devices and the server to understand who is still online. And so they use digital signatures, for example, to assess that this group of users is still online, and we will rely on them until the end for aggregation.
Looks very much like a classical distributed system, like in the field of distributed systems, like Rashid Garawi and these people. So my question is, on what type of communication does this feel like? Do you need broadcast?
Yeah, they do a public infrastructure at the beginning. So the devices have registered officially to the server, and they know their identity, and the public key is bound to their identity. So it's like on the internet.
It was more like synchronous versus asynchronous.
Ah, okay, sorry. Yes, here there is an idea of synchronicity. It's one round, one training, and you respect the steps. So you receive a global model, you train, you get a result, and then you perform aggregation, and the steps are ordered and respected. Does that answer the question?
Kind of, but we can.
Toujours dans le synchroniste ou asynchrone, est-ce que les données, est-ce qu'il va pouvoir utiliser celui du milieu? Est-ce qu'il va pouvoir partager ses mises à jour au prochain round ou c'est perdu?
In that case, it's lost. We will ask him to wait for the new blue model, here from blue and green, and to train on that one. But that's exactly what I will present. One of the limitations we want to overcome. Indeed, is slow, it will probably train for nothing. Now we show you what has been done in the same way, but for additively homomorphic encryption. So here we have the additive property for both the keys and the plain text, the inputs from the clients. So we can sum the key, and it becomes the aggregation key, and that aggregation key is accessible to the server, and so it will decrypt the global model and get it in play. And the messages represent the local inputs from the client, so the device blue, device red, device green, and it gives a global model containing all the inputs from the clients who participated. So secure aggregation with additively homomorphic encryption. So you encrypt your model using your key, your own key, and we have the sum on the individual input that gives a new global model, and we have the sum on the keys that gives the aggregation key. And again, everyone participated as expected. Device red. Again, failed. So, of course, I can add the local inputs from device blue and device green. I get the global model from blue and green, like for masking. But I cannot put the aggregation key because I miss the key from red. So the server cannot decrypt. That they cannot recover. So we get something that is not usable. Again. So similarly, for masking, you secret share your keys in case you will fail. So you do that at the beginning when you are registering with everyone else. So red key shares key with all other devices in the system. And in case red failed, so in addition to sending the local input encrypted with the key, the blue key and the red key, it's like you encrypt a null message with the key share from the device red, and so you sum for shares, you get the red key, and then you sum all the keys, and you get the aggregation key. And like for masking, it's an empty message, it doesn't matter. We still get a global model, but with contribution from blue and green only. And similarly, red did the job for nothing. Yes, again.
If no clients failed, nothing gets shared, right? The clients don't send shares of their secrets.
If nobody fails,
Yeah.
they share at the really beginning during the setup phase in case of a branch.
And then to the server.
Yeah, between them, through the server, because the server tells them who will participate in that system. But in case red, here the picture is indeed because blue and green has been told by the server that red is not participating, so they need to give the information they have from red.
Only that.
Yeah. If the server tells them that red is participating, you don't need to include that pieces, those pieces.
Question I have is, so what is a server? Is like, so it's telling to blue and green that red is not there, and telling to red and green that blue is not there. Can you like?
So that's why there are many communication rounds until everybody agrees on the same set of online clients.
So, but by that time, maybe some other client will have dropped.
Indeed, but that is another problem. So we just before, so when that happens, they have agreed on a set of group of the clients, telling the server that indeed they will participate until the end. Indeed, blue can drop until he has just said to the server, yes, I will participate until the end, and then he doesn't participate, then we are stuck.
Other question I had is, so you said there is a lot of.
Yes. Yes, there are a lot of back and forth.
Can you like in advance imagine the scenario where maybe your head will fail or other, and like prepare stuff that you send all together just in case, so you don't need to, like a normal time to wait.
Yeah, this is what I will present. But indeed now the solutions I presented were the first ones, but now we have what they have called for some of them one-shot communication. So we just ask the clients to submit their inputs if they are ready, and after we don't, the clients can disappear, the server has enough material to keep on until the end.
Donc, parce que
Oui.
il y a le modèle de défaillance, ok, mais et le modèle de sécurité, est-ce que tu pourrais nous le dire, que celui qui est classiquement admis dans ce domaine, parce que classiquement là on voit deux soucis, c'est collusion entre les clients, ou même le serveur, il a la somme des clés, il a la clé.
But it doesn't matter if he gets the aggregation key at the end is what he wants. And you get fresh keys at every round, so it's not because you can use, you don't have to play attacks.
Pendant symétrique ou asymétrique?
For that is, that stage is public key. But you have some symmetric keys to construct the pairwise information. So the security model is honest and spurious. So it follows the protocol as expected, but try to get some information. It's 1/3 of online honest clients. Malicious, so we try to take it from the protocol. 2/3 of honest online clients.
Don't call it.
They don't call it.
And still the keys given to the server, it appeals me. Like with the blue share, the red share, and the green share of the keys, the server cannot decrypt the blue brain, the blue model, individual model.
So the shares are not built on the same polynomials,
Yes,
so you cannot get proper key from shares from different polynomials. was your remark?
Non, la clé bleue, la clé rouge reconstruite à partir des deux shares et la clé verte, qui font la somme de la clé noire. Est-ce que ça peut pas être utilisé pour déchiffrer le modèle individuel ou ouvert ou la contribution individuelle du bleu?
So using a red, the green, and
Tout ce qu'il a, il a tout.
Non,
Il a la bleue, la verte, la rouge, quoi. Donc il peut déchiffrer le.
maybe he doesn't see the shares because they are encrypting message. Null message. They are not given. It's not a key given in clear. They are encrypting the message. So you see a ciphertext, but the ciphertext doesn't contain something useful for the global model.
Tu as dit tout à l'heure que le serveur déchiffrait le global model.
Using that key, he gets that key. He will ask for the online client to reconstruct that key. This being, of course, maybe if we have two keys, just the difference. Maybe still, suppose that you need some information from one of the two in order to get the subtraction, let's say black minus blue. Well, but the linear combination of the keys is there are too many unknowns.
Okay. We discuss that.
If
So if I understand correctly, the left view is reconstructed by the clients.
It's reconstructed by the server by using the help path with the help of the clients.
So he is able to reconstruct the black key without seeing the contribution.
Yeah. So he has access to that key, but the scheme is very subject to cannot get access to the individual keys. We in the solutions I show you, we need to reconstruct the missing information. So red, the device red missed the round. So we needed the blue and green that are still online to reconstruct the information from red to complete the aggregation. So to reconstruct the masks that were missing or to reconstruct the encryption from the red key. But us, we try to develop solutions where if a client fails, it doesn't matter. We just rely on the remaining clients, the online ones, but just using their own information. You don't ask them to reconstruct the missing information from the device thread. Okay, so we have two types of federated learning. So synchronous is what I showed you. Devices train on a global model at a given round. They get a result, they submit that result, they wait for aggregation, and once aggregation happens, they get a new global model and they train on that new model, and so on. But there is a round that is defined and they follow the steps through that round. So it's synchronous federated learning. So we got Eagle, our first solution, and then we got Paul and Buffalo, that is buffered asynchronous federated learning. So here we have finally more devices, and we have a buffer that accepts up to 5 contributions, and once we get 5, we trigger aggregation. And so 5 clients submit their contributions, their results, and so it goes to the buffer, and so the aggregation happens because we get 5 and we get a new model. So we cannot get fully asynchronous because it means that aggregation will happen as soon as you get a new contribution. So it will be too easy for the server to get individual inputs, since it could simply subtract the new global model with the previous global model. So we have a buffer to have enough inputs in order to hide your own local input. Yes.
Question rapide, est-ce que c'est dès qu'il y en a 5 qu'il y a l'agrégation? Fait que s'il y en a des points, ils vont toujours être livrés.
So you design your system and you put a threshold. For my example, it's 5. But indeed, if I have 5, the 5th comes and suddenly there is a 6th, but the 6th is for the next buffer. Because in that case, yeah, maybe I can tell right now because you asked. So when it's synchronized, you assess if the device head has been training on the current global model, but it was just too slow. So his training is lost. He needs to wait for the new global model and train on that one. For buffers asynchronous federated learning, at least for us, we don't care on which global model the client has been training on. So maybe device orange is using the most recent training global model because it's a fast device. But maybe purple is really slow, and so it's an older global model. But the design subject doesn't matter. There is no parameter representing the formal rank in the system. They have their own individual ranks of training included in their information. So doing so, even if you are slow, your training is not lost. At least the resources you put into training, they are not lost. So Eagle. Secure aggregation, because the server tries to infer information from the individual inputs from clients. So we use additive homomorphic encryption, and the scheme is called John Bet. And we wanted to avoid reconstructing the information from the drop clients. So for the clients who failed to submit their input by the end of the round, because remember we are in the synchronous federated learning context, it's okay. The online clients rely on threshold additive homomorphic encryption, so it's a threshold variant of the join leader scheme. And so threshold means that in addition to the encryption scheme, we have secret sharing techniques included in that encryption scheme. And so at the beginning, when you set up your threshold additive homomorphic encryption, you prepare secret sharing with NPCs, and you have the threshold T that says, I need T online clients to complete decryption using that scheme. So it's the same scheme than above to protect the inputs, but with the threshold, meaning that we use secret sharing techniques, we need T out of the N total clients. But don't go into details, in free questions. So as I said, we are in the synchronous federated learning context. So there is the idea of client failing because they don't submit their inputs on time, but we just need the remaining clients to complete aggregation with the server. So they just share with the clients their own information. We don't need to reconstruct the information from the drop clients. And so they have keys for each round. Here the round is the same for everyone. So we need to track the round where training happens. So it should be shared, should be the same for every client. Showing they are training on the same model. And then the aggregation key that is given to the given is but for the server to recover the global model is used using information from the online clients only. And indeed, you can recover the global model because you decrypt with the aggregations. Then we have all, and so here we start with the same thing as for Eagle. We encrypt the inputs from clients using the join scheme. But here, instead of using the threshold additively homomorphic encryption scheme, we combine buffer and secret sharing techniques. So there is no encryption step. Remember the threshold join scheme, there is secret sharing embedded into it. But here we simplify a little bit because we just use the secret sharing techniques directly and the idea of buffer. So buffer means you wait for enough contributions. So I said 5 earlier, it could be another number. And then the shares shared between the online clients will be used to finalize the aggregation. And we use the first scheme using secret sharing. Yeah.
In the buffer, can you end up using twice the amount submitted by the same client?
So if it's twice the same ciphertext, no, we will see it, but after we cannot prevent a client from using twice the same input. Oh, maybe you don't understand the question. Is one client same input or two clients same input?
Well, client two inputs, one client, two inputs at different times. If you wait, say, the way I understood buffer is you wait until, say, X client submitted. Donc, during that time period, the same client could have submitted two versions.
So for one buffer, one client submit twice, that we can prevent. But we cannot prevent the client submitting twice the same input for two different buffers. And so, yeah, buffer this time for all, so we wait for enough contribution. And so here the clients, so there is no round, formal round, like it's not because we allow the clients to train at their own pace. Some are really fast, so they have more training rounds than others, so they have their own round defined. But so for every round they have a new key, and so they secretly share that key with other clients. And you can reconstruct the aggregation key that is the sum of those keys based on online clients, because we have been using secretly sharing techniques, secret sharing techniques. We don't need all the clients, 3 of them are enough to reconstruct the keys of those online clients, and so it's enough to get the aggregation key. So it's the same, we don't need all clients to get the aggregation key, 3 of them are enough because of the secret sharing techniques.
This case, because there is no round, could it happen that some client work on a very old model and try to
we allow that.
And at the end you can like decide on what is the final food model that people should be, or it's like if it's not an issue that the
you can repeat the experiments. Apparently the accuracy was not it was not slower to reach good accuracy than in the synchronous version. He tried to show that.
Maybe another question, the scale of model, I would go to the same question as Marco. So when did people in federated learning start to think about like asynchronous and buffer? Was it directly when they started to work on federated learning, or is it something like more recent that people have? So for example, I imagine where if you take the use case where you have millions of smartphones, it's likely that you will have people failing. So is it something that they start to imagine since the beginning, or is more recent?
Almost from the beginning, is they were thinking about that, and their solution was to over-select. So they wanted 100 clients, and they say we need 30% more of them at the beginning to be sure that we can complete aggregation. They did that in that way.
Pretty much another thing you can do is you say the world is going to last 1 week, and even if people disconnect, at some point they will reconnect.
You mean, I mean, at the beginning they were in the synchronous version, so they
Yes.
finally they were excluding the slower clients. It would be that it's more. So it's true. So from the beginning, they thought about clients disconnecting during the process, and so how to overcome clients who drop. But it came later that maybe their contributions are still valuable. We should include them in some way.
If I may, Sebastian, the classical figure model is very safe, so the client who fails doesn't come back. Usually in the classical distributed system.
Yeah, but in Federated Learning,
you don't know if the buffer is more fuzzy.
Yeah. Sorry. Sorry, I showed that. And the last solution, Buffalo. So first we use encryption to protect the inputs from the server. But here Ricardo wanted to improve that encryption step, because remember that we need to secret share keys, like for all. So because of that part, until now we were using JoinLibert to encrypt the individual models that are really large vectors. And so Ricardo proposed to first use learning with error, a lattice-based skill, post-counting by the way. And then use JoinLibert on the keys we used to encrypt the models that are much smaller than the models, and to secretly share those keys. So instead of sharing a vector, you share a scalar. So it was more efficient. And so, like all, we use a buffer in case you fail to submit your update on time, even if so it's from the synchronous context. There is no time anymore, but so you submit when you are ready. But then, because we were still asking for the clients who submit something to the buffer to be ready for the next step for completing the aggregation. Maybe between they can drop. So even if they have submitted some updates, they fail after, they become offline, so they cannot help the server to complete aggregation. So we introduced assistants that we assume more powerful than the regular clients, and secret sharing lab. And so the assistants are the super clients who will help the server to complete aggregation. So we did not invent that rule. It came from the literature review. There are several solutions to make the Federated Learning protocol more efficient, asking a bunch of special clients to assist the server instead of the random clients. So quickly, Buffalo. So as all, we have a buffer, and we wait until the buffer is full to trigger aggregation. We only rely on the clients who submitted something at the beginning, but I say that, but then it's not true, because as I said, we have assistants. So you submit something, but we ask the client to share information with the assistant at the moment they submit their inputs to the buffer. And using for share, the assistant will help the server to reconstruct the aggregation key. We use double encryption for performance reasons because the models to encrypt are really, really large. And so that is similar to all. We use secret sharing techniques. So the clients secretly share their keys not with other clients, but with their assistants, and the assistants are here to help the server to reconstruct the aggregation. Yeah.
Assistants and multiple clients at the same time, or simply one not clients on the system.
Yeah, every client the channel with one assistant. But it doesn't change much compared to other solutions, because when we don't have assistant, we are supposing anyway that the client has some pairwise information with every other client. So instead of having every other client, in that case, it's every other assistant. That should be a smaller group than the clients. One.
And we require the assistants to be online.
Yeah,
They can
the solution is stronger. So when we define the role of assistant, we say that they are much more reliable than the regular clients.
C'est juste le titre de l'article, là, Stragglers, je sais pas si ça me va.
Is actually, this is what we call slow clients. So it's what we call when they fail to submit something, and plus when they are not here to complete aggregation. Yeah, it comes from one paper in the literature, but it's the name we used in our paper. Yeah.
I wasn't sure what the double encryption is for. Is the second scheme just encrypting the keys of the first?
So for here, the double encryption.
Yeah, what was that for?
C'est for performance reason. The two first, two previous schemes, they are just using joy-libert.
Yeah.
And joy-libert doesn't perform well on really large models. We need to secret share the keys.
Okay, so the addition is faster?
Yeah, because we still use joy-libert. It's the scheme we want to use to get our additive homomorphism.
So we only encrypt the keys?
Those keys are much smaller. And so after to secret share, it's a scalar instead of a vector. So it's just for performance reason. It's still better to get two encryption steps and secret share from smaller inputs than to get only one encryption but big plain text. Yeah. And that's it. The summary of the three solutions. Yeah. Any other questions? Oh, really? Yes.
Est-ce qu'il y a des questions en ligne?
Peut-être les lire sur le chat. Voilà.
Oui, bonjour. Bonjour.
Oui, je vous entends.
Est-ce que vous... D'accord, merci. I will ask my questions in English. So thank you very much for the presentation. I have a couple of comments. So maybe I missed a little bit of the beginning of the presentation. Now, when you put the aggregation, you put the side, you just put them one just beside the other one. But for aggregation, usually we have an average or we have a gradient that you usually make an average. Let's say the simplest solution is to have an average. So it's better maybe to put it in a different color, because it's not just putting these three different colors like one just next to each other. So it should be transformed, right? So it's just a minor remark. Now,
to say the way I illustrate the global model, maybe.
Exactly.
Okay.
Yes, it is a little bit confusing because it's not transformed. It's like you are just collecting those gradients and you are just like putting them in the model. Like they are updating different weights. It's not the same, like the same weights. Now, in terms of architecture,
Actually, I don't use weights. It's a RID version. We assume the data are all balanced.
okay, but it is transformed somehow. So you have an average or some computation. So it's not exactly like the red is no longer the red in the final model. Yes. So this is my point. Okay. Now, in terms of architecture, here you are selecting a two-tier architecture, right?
Sorry, I didn't get it.
It is a two-tier architecture. You have the clients that can join and leave, like at any time, like in Internet of Things. And you have the server, which is the cloud. Let's say this is the cloud. All right. Now, your assumption. So here, what I'm missing maybe from your presentation is the assumption. So I think you need to make a lot of assumptions about like the security of the server, the client. So can the client, for instance, or these like mobile phones or Internet of Things, can these be compromised, for instance? Because because the folks, no. So, okay.
But I don't know. I won't say it's Internet of Things environment. They cannot leave. But they can leave if they don't want to participate, but they don't really leave the system, but they need to join at the beginning. It's static.
Okay, it's static. So I know that I have a certain number of clients that would contribute to my model.
Yeah.
Okay, and those are, which should be like honest, like
but curious.
participants.
They're honest but curious. But for we have up to maybe you missed Marco at the question. We have when the server is honest but curious, we need 1/3 of honest online clients, and when the server is malicious, we need 2/3 of honest online clients.
Okay, great. Now you were talking about initialization. So the initialization between the clients themselves, they exchange their keys, or can you elaborate more on this?
They indeed share information. They secret share their keys with others. They have some pairwise keys. So every client has a key shared with another client, and they use those symmetric keys to share what they need to share in order to complete the reconstruction of the aggregation key at the end.
Okay, great. Now you just talked about the first part of the federated learning. So you are just sending now the the gradient or the weights to the server. But what about the other way around? It is bidirectional. Now the server has done the aggregation and then created the new model, right? Then this new model needs to be downloaded back to the clients. So which cryptography, which security are you using now on the other in the other way?
So Eagle, they don't have anything for that. They don't check the received global model. But Buffalo, we combined hashing commitments and digital signatures to let the homomorphic hashing and homomorphic commitments to let the clients check that their contribution were included in the new model.
Okay. Thank you very much.
Thank you.
Maybe a naive question. How do you assess that your proposals are correct? Can you deploy this type of secure aggregation on real-world data and machine learning algorithms to prove that it works?
So from a security point of view, it's theoretical. So I think there will be always a debate until someone breaks the scheme. But from the machine learning point of view, Ricardo, the main author of those contributions, did some experiments. So he used data sets that are public, like MNIST. So it's that the picture of numbers, cipher, I think images. And he had also access to medical data sets because he was funded by it was a joint project with hospitals in south of France. So yeah, he used those data sets to launch his solutions, and accuracy was close to what we could get without using our solutions.
Yeah, and actually, I was wondering the assumptions you make may not introduce some biases on the clients, you know, when you are just taking into account the first T clients which are ready. In this case, is there a risk that you favor the clients which have more power, computational power, or more training data, or?
It could be that Buffalo, the last solution, so when he asked which kind of new global model the clients received, because we started with the idea that the server will aggregate some inputs and will aggregate different inputs and send the first model to some clients and the second model, so different global models. So it's why we included some verifiability steps. It's more for Buffalo. So the client submits an update, so he expects that his update will reach the buffer and will be included for aggregation. And so by receiving the new global model, he will check indeed if his own contribution has been used for aggregation. So after, we cannot prevent the server to favor some, but some clients can at least notice what he has been doing. And so maybe on top of that, we can put a complaint process to cancel.
Just propose to include this equity and fairness as to evaluate this type of protocol.
Yeah, good idea indeed. Yeah.
Are there any more questions online? Est-ce qu'il y a d'autres questions en ligne? Je pense que c'est bien. Et dans la salle aussi, peu de questions? Dernière question?
I have a general question. When we refer to secure federated learning, it's more about protecting the integrity of the client and the server and building kind of trust mechanism. There are some other areas, research areas. I'm new to this area.
So I think, yeah, the first goal was to protect individual inputs from the server. But indeed, now there are some integrity rules. So, for example, you have what they call robustness, so we check that the inputs from clients are not malicious. So it's kind of we compare as you can, because even it's competitive, it's that their inputs are within a certain range. So maybe it would be just an outlier. Maybe it's a client is honest, but its input is weird. That is also on the other side, maybe try to poison the model. And for the server, as I could say, value use commitments. And for example, to check that the server its ability as expected. Thank you.